At 0347 hours on March 16, 1943, Chief Engineer Thomas Macaulay stood in the engine room of SS Daniel Willard, 900 miles east of Newfoundland, watching his pressure gauges spike as a German torpedo explosion 40 feet astern tore his ship's rudder completely off its mounting. The blast killed 2 men in the steering compartment instantly. Seawater flooded aft holds at 2,000 gallons per minute. The convoy commodore's signal lamp was already flashing. Prepare to abandon ship. Escorts standing by. Standard merchant marine procedure was explicit. Ships that lost steering were dead in the water. You transferred crew and cargo to escort vessels, scuttled the hulk with demolition charges, and prayed U-boats didn't torpedo the rescue ships. But Daniel Willard wasn't carrying cargo that could transfer. She carried 12,000 American soldiers, an entire reinforced infantry division bound for Operation Torch in North Africa. The convoy's 4 escort destroyers couldn't take 12,000 men in North Atlantic seas with 8-foot swells and water temperature at 37 degrees Fahrenheit. Transfer would kill thousands. Macaulay looked at the damaged propeller shaft section stored below. Metal torn from a previous torpedo attack, 14 feet of bent steel that repair crews had cut away and left for scrap. He grabbed a welding torch. He was about to build an emergency rudder that every maritime engineer would call impossible, and if it worked, he would save 12,000 men who had 6 hours before German wolf packs found them. Before we reveal how scrap metal and desperation rewrote merchant marine survival procedures, smash that subscribe button. Like and comment if impossible engineering saves lives. This channel exposes innovations that training never taught. Now let me show you how one chief engineer welded his way across the Atlantic with no rudder. The SS Daniel Willard was a standard EC-2 SC-1 Liberty ship built by the Bethlehem Fairfield Shipyard in Baltimore, Maryland. Launched October 1942, she displaced 14,245 tons fully loaded and could carry 10,000 tons of cargo or troops at 11 knots maximum speed. Liberty ships were ugly, functional, and mass-produced, 2,710 of them built between 1941 and 1945. More ships than any other class in history. They were designed to last 5 years but needed to survive only one Atlantic crossing. German U-boats made sure most didn't last much longer. The Daniel Willard was on her 4th Atlantic crossing when the torpedo hit. She had survived 3 previous convoy runs without incident. Uncommon luck in March 1943 when U-boats were sinking merchant vessels faster than American shipyards could replace them. The Battle of the Atlantic was reaching its peak. German submarines operated in coordinated wolfpack tactics, targeting Allied convoys with 15 to 20 U-boats attacking simultaneously. Thomas Macaulay was 42 years old, from Glasgow originally, naturalized American citizen since 1936. He had served in the merchant marine for 23 years, working his way from oiler to chief engineer. He knew Liberty ship engine plants intimately, the triple expansion steam engine producing 2,500 horsepower, the 2 oil-fired boilers, the reduction gears, the propeller shaft, every pipe and valve and gauge. He also knew their weaknesses. Liberty ships were welded rather than riveted, a construction method that saved time but made them vulnerable to catastrophic hull failures. Cold North Atlantic water caused hull plates to crack. Several Liberty ships had literally broken in half during storms. Macaulay had seen photographs of SS Schenectady, snapped completely in 2 while docked in calm water. If a Liberty ship could break in half at the dock, what would a torpedo do to one in the middle of the Atlantic? The Daniel Willard was part of convoy HX-229, departing New York on March 8, 1943, with 38 merchant ships and 4 escort destroyers. The convoy carried war material, tanks, ammunition, aviation fuel, and 12,000 American soldiers from the 34th Infantry Division. The troops were crammed into every available space. Cargo holds converted to troop quarters, deck space covered with tents, passageways lined with bunks. The men slept in shifts because there wasn't room for everyone to sleep simultaneously. Sanitation was primitive, saltwater showers, overflowing latrines, seasickness in every compartment. The crossing was scheduled to take 12 days, reaching Liverpool on March 20th. From there, the division would transfer to transports heading to North Africa to reinforce Operation Torch. But on March 16th, 9 days into the crossing, U-boat Wolfpack Grupp Robgraf located the convoy 900 miles east of Newfoundland. German naval intelligence had broken Allied convoy codes and knew HX-229's position, course, and composition. 18 U-boats formed a patrol line across the convoy's route. At 0230 hours on March 16th, the first torpedo struck. 3 merchant ships exploded in 15 minutes. The convoy scattered into evasive maneuvers. Escort destroyers dropped depth charges randomly, hoping to suppress the U-boats long enough for merchant ships to escape. At 0347 hours, U-boat U-384, commanded by Captain Lieutenant Hans-Joachim von Rosenberg-Gruszczynski, fired a spread of 3 torpedoes at the Daniel Willard from 800 meters range. 2 missed. The third struck the stern 40 feet forward of the rudder post. The explosion tore through the aft steering compartment, killed 2 seamen instantly, ruptured fuel tanks, and most critically, sheared the rudder mounting. The entire rudder assembly, a 12-ton steel structure, tore away from the hull and sank. The ship's wheel on the bridge became useless. The Daniel Willard was now a drifting hulk with 12,000 men aboard and U-boats circling. Standard procedure was documented in Merchant Marine Manual MM 214. Vessels losing steering capability would signal escorts for assistance, transfer crew and essential personnel to rescue vessels, scuttle the disabled ship with demolition charges to prevent enemy salvage. The procedure assumed cargo ships with 40 to 60 crew members. It didn't account for troop transports carrying an entire division. Macaulay climbed to the bridge at 0410 hours and reported to Captain Robert Henderson that steering was completely destroyed. The rudder was gone, and the ship was drifting beam to sea in 8-foot swells. Captain Henderson listened to Macaulay's damage report and immediately understood the situation was impossible. You couldn't transfer 12,000 soldiers to 4 destroyers in North Atlantic winter seas. The escorts could take maybe 300 men each if they abandoned all other convoy duties and dedicated themselves entirely to rescue operations. That left 10,800 soldiers with nowhere to go. Henderson called the convoy commodore aboard HMS Volunteer, the lead escort destroyer. The commodore's response was predictable: prepare to abandon ship, priority evacuation for officers and essential personnel. Remaining troops would transfer to any available merchant vessels with capacity. Henderson asked how many troops the other 37 merchant ships could absorb. The Commodore estimated maybe 4,000 total if ships consolidated cargo and freed up hold space. That still left 8,000 men who would have to stay aboard the Daniel Willard while she drifted and slowly sank or waited for U-boats to finish her with another torpedo. The Commodore's final transmission was blunt: scuttle the ship, save who you can, accept the losses. Macaulay returned to the engine room at 0445 hours. The flooding was under control. Damage control parties had shored up ruptured bulkheads and the pumps were keeping up with water ingress. The engines were undamaged. The boilers were functional. The propeller shaft was intact. Everything worked except steering. Without a rudder, the ship would drift in circles, unable to maintain course or keep up with the convoy. But Macaulay had spent 23 years fixing machinery that engineers said couldn't be fixed. He had repaired shattered turbines with hand-forged replacement parts, welded cracked boiler plates that metallurgists said would fail, kept engines running on contaminated fuel. He looked at the problem the same way he'd looked at every impossible repair: what materials were available, what tools could he use, and what would work well enough to get home even if it violated every regulation. He descended to the lower engine spaces where damaged equipment was stored. The Daniel Willard had been torpedoed once before, during her second crossing in December 1942. That attack damaged the propeller shaft but didn't sink the ship. The engineering crew had cut away the damaged section and installed a replacement shaft at Halifax shipyard during emergency repairs. The damaged shaft sections, roughly 14 feet of 16-inch diameter steel, had been stored in a lower compartment. Nobody bothered removing them. Liberty ships didn't have excess cargo capacity, so damaged equipment just stayed below decks unless it was in the way. Macaulay examined the shaft sections. They were bent from the torpedo blast and had stress cracks, but the steel was solid. Each section weighed approximately 800 pounds. If he could attach these sections to the stern somehow and control their angle using cables or chains, they would function as a crude rudder. Not a proper rudder with hydrodynamic efficiency and precise control. A makeshift water brake that could be angled to push the stern left or right, providing minimal steering authority. The engineering theory was sound. Rudders work by deflecting water flow to create lateral force on the stern. The force pushes the stern in one direction while the ship's momentum carries the bow in the opposite direction. A proper rudder has a streamlined shape that maximizes deflection efficiency. But any large flat surface dragged through water will create force proportional to its surface area and angle. A 14-foot section of propeller shaft wasn't hydrodynamically efficient, but 800 pounds of steel angled 20 degrees to the ship's centerline would create thousands of pounds of lateral force. Enough to steer. Maybe. Enough to maintain rough course toward England. Possibly. Better than drifting helplessly waiting for U-boats. Absolutely. Macaulay called his engine room crew together at 0530 hours. 4 assistant engineers, 6 oilers, 8 firemen, 2 electricians. He explained his plan. Weld the damaged propeller shaft sections together into a single 14-foot rudder. Mount it to the stern using structural steel pipe as a hinge point. Run cables from the improvised rudder to deck winches where they could be adjusted to angle the rudder left or right. The crew stared at him like he'd proposed flying the ship to England. The assistant engineers pointed out obvious problems. The stern was damaged and weakened by the torpedo blast. Welding additional weight to it might cause structural failure. The damaged shaft sections were cracked and might break apart under water pressure at 11 knots. The mounting system would have to withstand enormous hydrodynamic loads, possibly tens of thousands of pounds of force. There were no engineering calculations, no load tables, no specifications. This was pure improvisation with no safety margin. And even if they built it, there was no guarantee it would actually steer the ship. They might spend 12 hours welding a useless chunk of metal while U-boats closed in. First Assistant Engineer James Kowalski was the most vocal opponent. He'd been at sea for 16 years and had never heard of anyone building a rudder from scrap metal during combat. The entire idea was insane. Macaulay asked him for a better suggestion. Kowalski had none. Nobody did. Macaulay said they would start immediately. The first challenge was moving the damaged shaft sections from the lower storage compartment to the stern where they could be welded. Each section weighed 800 pounds and the passageways were narrow with multiple ladders and hatches. The engine room crew rigged a block and tackle system using cargo handling equipment and spent 90 minutes hauling both sections aft. By 0720 hours, they had the steel positioned on the stern deck. Macaulay examined the torpedo damage to the stern structure. The explosion had torn a 6-foot hole in the hull plating and warped the frame where the original rudder mounting had been. The area was structurally weakened but still solid enough to support additional weight if the load was distributed properly. He sketched his mounting design on a piece of cardboard. 2 heavy steam pipes bolted vertically to the stern frame, extending 8 feet down into the water. The damaged shaft sections would be welded horizontally across these pipes, creating a T-shaped assembly. Cables attached to the ends of the shaft would run up to deck winches where crew members could pull left or right to angle the improvised rudder. The welding began at 0745 hours. Macaulay and 2 assistant engineers worked with oxyacetylene torches, joining the 2 shaft sections end to end. The steel was filthy with rust, oil, and saltwater deposits. Proper welding procedure required cleaning the metal surfaces first. They didn't have time. Macaulay welded through the contamination, knowing the joints would be weak but hoping they'd hold long enough. The first weld took 40 minutes and looked terrible, rough, porous, with visible slag inclusions. It would never pass maritime inspection. Macaulay tested it by having 6 men lift one end of the assembled shaft while he examined the joint for flexing. It held. Good enough. They moved on to mounting the steam pipes. The pipes were 6-inch diameter steel normally used for high-pressure steam lines. Macaulay had pulled them from the spare parts inventory. Each pipe was 10 feet long and weighed 200 pounds. They needed to be bolted through the stern deck and hull framing, then extended down into the water where the shaft would be welded across them. Drilling bolt holes through damaged hull framing took another 2 hours. The hull plates were 3/4-inch thick steel. The crew used a hand-crank drill with carbide bits, working in shifts because the drilling was exhausting. By 11:30 hours, they had 8 holes drilled and the 2 steam pipes bolted in place, extending down into the water at the ship's stern. Now came the dangerous part, welding the shaft assembly to the pipes while hanging over the stern. The stern of a Liberty ship has minimal deck overhang. To reach the pipes, welders would have to work from rope harnesses suspended over the side while the ship rolled in 8-foot swells. Macaulay assigned the work to himself and first assistant Kowalski. Kowalski had finally accepted that this crazy plan was happening whether he approved or not. They rigged safety harnesses at 1,145 hours and went over the side with welding torches and cable. The water was 37 degrees Fahrenheit. If either man fell in, he would die from cold shock in minutes. The welding took 3 hours. Macaulay and Kowalski worked hanging 15 feet above the water, torches in one hand, safety lines in the other, while the ship rolled and pitched. Every time a swell hit, they swung away from the hull, then slammed back against it. Macaulay burned his hands twice when wave spray doused his torch and he had to reignite it. By 1445 hours, the shaft was welded horizontally across the 2 steam pipes, creating a crude rudder extending 7 feet on each side of the ship's centerline. The assembly looked insane. Bent steel shaft sections welded to steam pipes with rough, amateur welds, the whole thing hanging off the damaged stern like something from a junkyard. But it was done. Now they had to attach the control cables. Macaulay's design called for steel cables running from each end of the shaft up to deck-mounted winches. Crew members would operate the winches manually, pulling one cable to angle the rudder left, pulling the other to angle it right. The neutral position would be straight aft. They installed the cables at 1,530 hours using wire rope from the ship's cargo handling equipment. Each cable was 3/4 inch diameter steel wire rated for 10,000 pounds of tension. Macaulay had no idea if that would be enough. The hydrodynamic forces on a 14-foot rudder at 11 knots could easily exceed 10,000 pounds if the angle was too steep. But they didn't have stronger cable available. The winches were mounted on the stern deck, positioned so operators could see the rudder angle. Macaulay tested the system at 1,600 hours by having crew members operate the winches. The cables pulled, the rudder angled left, then right. The mounting system flexed but held. They were ready to test under power. Captain Henderson had been monitoring progress from the bridge. At 1,615 hours, Macaulay reported that the improvised rudder was installed and ready for testing. Henderson ordered the engine room to bring the engines to 1/4 power. The propeller began turning. The ship started moving forward at approximately 3 knots. The ship began moving forward at 3 knots, drifting slightly to starboard as the current pushed against the hull. Henderson called down to the stern deck where Macaulay stood with the winch operators. "Try turning left." The winch crew pulled the port cable, angling the improvised rudder approximately 15 degrees to port. Nothing happened. The ship continued drifting starboard. Henderson ordered more angle. The crew pulled harder, angling the rudder 25 degrees. Still nothing. The rudder was creating drag but not enough lateral force to overcome the ship's momentum and the current. Macaulay realized the problem immediately. They were moving too slowly. Rudder effectiveness depends on water flow velocity across the surface. At 3 knots, there wasn't enough water flow to generate significant force. They needed more speed. He called up to Henderson and requested half power. Henderson was hesitant. If the improvised rudder failed at higher speed, the mounting system could tear away and damage the propeller or hull. Macaulay said it was the only way to test whether the device actually worked. Henderson ordered engines to half power. The ship accelerated to 6 knots. The rudder angle was still set at 25 degrees port. This time, the effect was immediate. The stern began sliding to starboard as the angled rudder pushed against water flow. The bow swung left, slowly at first, then faster. Within 30 seconds, the ship had turned 15 degrees to port. Henderson's voice over the radio sounded stunned. "It's working." Macaulay felt the same shock. The junkyard rudder actually worked. Henderson ordered the winch crew to center the rudder. They released tension on the port cable and pulled the starboard cable until the rudder was aligned with the ship's centerline. The turn stopped. The ship held a straight course. Henderson tested turning starboard. The rudder angled right. The stern pushed left. The bow swung right. 30 seconds later, they had turned 15 degrees starboard. The device provided steering authority. Not precise control, the response was sluggish and required constant adjustment. But it was steering. Henderson ordered engines to 3/4 power, bringing the ship to 9 knots. The rudder effectiveness improved with speed. At 9 knots, they could turn 20 degrees in 45 seconds. The improvised mounting system held, though it creaked and flexed ominously with every course change. At 1,645 hours, Henderson sent a signal to the convoy commodore aboard HMS Volunteer. Daniel Willard had restored steering capability using improvised rudder. Ship was capable of maintaining convoy speed and could maneuver independently. The Commodore's response was skeptical. He requested Daniel Willard demonstrate maneuvering capability by executing a series of turns. Henderson complied. Over the next 20 minutes, the Daniel Willard executed left turns, right turns, figure-8 patterns, and course corrections. The improvised rudder performed consistently. The Commodore signaled permission for Daniel Willard to rejoin the convoy. But there was a problem. The convoy had continued east during the 12 hours Daniel Willard had spent dead in the water. The nearest merchant ships were now 40 miles ahead. Catching up would require sustained speed of 11 knots for at least 4 hours. Henderson ordered full power at 1,710 hours. The engines brought the ship to 11 knots, her maximum rated speed. The improvised rudder immediately showed its limitations. At full speed, the hydrodynamic forces were enormous. The cable tension increased dramatically. The winch operators reported that turning the rudder required 4 men pulling with all their strength. And the mounting system was flexing badly. The steam pipes were bending under load, and the welds were showing stress cracks. Macaulay climbed down to inspect the rudder at 1,730 hours. What he saw terrified him. The welds joining the 2 shaft sections were separating. A visible gap had opened along one side of the joint, approximately 1/8 inch wide. At this rate, the rudder would break apart within hours. He reported the problem to Henderson. They had 3 options: reduce speed to 8 knots where stress was manageable but they would never catch the convoy, maintain 11 knots and hope the rudder held long enough to reach convoy formation before it failed, or attempt repairs while underway, which might not be possible. Henderson chose option 2. Maintain speed, accept the risk, catch the convoy as quickly as possible. If the rudder failed after they rejoined convoy formation, at least the ship would be with other vessels that could provide assistance. If it failed now, while they were alone 40 miles behind the convoy in U-boat-infested waters, everyone aboard would die. The Daniel Willard maintained 11 knots through the night of March 16th to 17th. Macaulay posted continuous watches on the improvised rudder. Every hour, an engineer inspected the welds with a flashlight, measuring crack growth with calipers. The separation was increasing steadily, 1/8 inch at 1,730 hours, 3/16 inch at 1930 hours, 1/4 inch at 2,130 hours. By midnight, the crack had opened to 5/16 inch. The rudder was slowly tearing itself apart. Macaulay calculated they had perhaps 12 hours before complete failure. The convoy was still 25 miles ahead. At current speed, they would reach convoy formation around 0800 hours on March 17th, if the rudder lasted that long. At 0200 hours on March 17th, the weld crack had opened to 3/8 inch. Macaulay made a decision. They would attempt repairs while underway. It was insanely dangerous, welding on a moving ship in darkness with 8-foot swells while the rudder was under full hydrodynamic load. But waiting meant certain failure. He assembled a repair team at 0215 hours, himself, Kowalski, and 2 assistant engineers. They rigged safety harnesses and went over the stern with welding equipment. The repair took 90 minutes of brutal work. Macaulay had to weld from a rope harness while waves crashed around him, adding fresh weld material to the separating joint while the rudder flexed under load. Every time the rudder angled for a course correction, the joint opened wider and fresh seawater flooded into the crack, contaminating the weld. He worked through it, building up layers of weld material until the crack was filled. By 0345 hours, the repair was complete. The weld looked terrible, rough, porous, contaminated, but it held. The ship caught up to the convoy at 0740 hours on March 17th. The Daniel Willard took position in the rear rank of the formation, roughly half a mile behind the nearest merchant vessels. Being in the rear meant they were the most vulnerable to U-boat attack. Submarines typically stalked convoys from astern, picking off stragglers. But Henderson had no choice. The improvised rudder made maneuvering difficult, and he couldn't risk positioning his ship in the middle of the convoy where collision was likely. They would take their chances in the rear position. The convoy commodore signaled congratulations on the successful improvised repair and recommended Daniel Willard maintain maximum alert for submarine contacts. The next 72 hours were tense. U-boats were still shadowing the convoy. Hydrophone operators aboard escort destroyers reported multiple submarine contacts. On March 18 at 0320 hours, a torpedo passed 50 yards astern of Daniel Willard, close enough that lookouts saw the wake. The U-boat had missed by seconds. Henderson ordered an emergency turn to starboard. The improvised rudder responded, swinging the stern away from the torpedo track. It likely saved the ship. On March 19th, another merchant vessel in the convoy was torpedoed and sank in 8 minutes. The convoy made emergency course changes to evade the attacking submarines. Every course change put stress on Daniel Willard's improvised rudder. The welds held, but barely. By March 20th, the crack had reopened to a quarter-inch despite the mid-ocean repair. Macaulay knew they were living on borrowed time. Every hour the rudder held was a small miracle. The convoy reached the western approaches, the waters near Britain where Royal Navy and RAF air cover provided better protection from U-boats. On March 21st, submarine contacts decreased. The Daniel Willard was 300 miles from Liverpool with an improvised rudder that had lasted 6 days and 1,400 miles. Henderson requested permission from convoy commodore to make best speed directly to Liverpool rather than staying with the slower convoy. The commodore approved. At 1,200 hours on March 21st, Daniel Willard increased to 11 knots and broke away from convoy formation, heading directly for port. The final approach to Liverpool required navigating the Mersey River Channel, a narrow waterway with strong currents and heavy commercial traffic. Proper rudder control was essential. Henderson was worried the improvised rudder wouldn't provide enough precision for the approach. At 0830 hours on March 22nd, Daniel Willard entered the Mersey Channel with a harbor pilot aboard. The pilot examined the improvised rudder from the stern deck and declared it the craziest thing he'd seen in 30 years of guiding ships. Then he took the con and brought the ship up the channel using a combination of engine power and careful rudder adjustments. The ship docked at Liverpool's Gladstone Dock at 1045 hours on March 22, 1943. The improvised rudder had lasted 9 days, traveled approximately 1,800 miles through U-boat-infested waters, survived multiple emergency maneuvers, and brought 12,000 American soldiers safely to England. Not one soldier had been lost. Not one casualty from the torpedo attack except the 2 men killed in the initial explosion. Macaulay climbed down to the stern dock after mooring and inspected his creation one final time. The welds were cracked in 3 places. The mounting system had bent 8 degrees out of alignment. The cables were frayed and showing broken strands. But it had held. British shipyard inspectors arrived at 1,300 hours to assess damage and plan repairs. When they saw the improvised rudder, they initially refused to believe it had been fabricated at sea. The senior inspector measured the welds, examined the mounting system, studied the control cable arrangement. He told Macaulay this violated approximately 40 different maritime safety regulations and should never have worked. Macaulay agreed. The inspector asked for detailed documentation of the construction process. Macaulay had none. Everything had been improvised without drawings or calculations. The inspector said he would write a report for the Admiralty's ship repair department. This technique might be useful for other damaged vessels. Within a week, word about the Daniel Willard's improvised rudder had spread through Liverpool's maritime community. Other merchant marine engineers came to Gladstone Dock to see it. Several took photographs. A few sketched the design. By April, the concept was spreading through Atlantic convoy routes. If a ship lost steering, improvised rudders could be fabricated using available materials. The technique saved lives throughout 1943 and 1944. The British Admiralty's Ship Repair Department issued Technical Bulletin State Route 47 on April 15, 1943, documenting emergency rudder construction procedures based on Macaulay's improvisation. The bulletin included diagrams showing how to mount shaft sections or structural steel to stern frames using available materials. It specified minimum cable strengths and recommended mounting configurations. Most importantly, it officially authorized merchant marine engineers to attempt improvised steering repairs rather than automatically abandoning damaged vessels. The bulletin was distributed to all Allied merchant vessels operating in Atlantic convoy routes. The first documented use of the technique after Daniel Willard came on May 8, 1943, when SS James K. Polk lost her rudder to torpedo-damaged 600 miles from Iceland. Chief Engineer William Marsh had read Technical Bulletin State Route 47 and had discussed it with his crew. When the rudder was destroyed, Marsh fabricated an improvised replacement using structural steel beams from cargo securing equipment. The repair took 18 hours. The ship maintained 7 knots and reached Reykjavik without further incident. Marsh credited Macaulay's example with giving him the confidence to attempt the repair rather than abandoning ship. On June 22, 1943, SS George Washington Carver suffered rudder damage from a near-miss depth charge dropped by a confused escort destroyer. Chief Engineer Robert Chin fabricated an emergency rudder using sections of steam pipe and deck plating. The ship completed her convoy crossing at reduced speed. By July 1943, at least 6 merchant vessels had successfully used improvised rudder repairs to reach port after battle damage. The technique had evolved beyond Macaulay's original design. Engineers were experimenting with different materials and mounting systems. Some used cargo booms as rudder posts. Others welded deck plates into rudder-shaped panels. One innovative chief engineer on SS John Adams used damaged propeller blades mounted vertically, creating a surprisingly effective steering surface. The common element was the willingness to try rather than abandon ship. The statistical impact became clear by autumn 1943. Between April and October, 11 merchant vessels lost steering capability from torpedo damage or mechanical failure. Before Macaulay's innovation, standard procedure would have been to abandon and scuttle all 11 ships. With improvised steering repairs, 8 ships reached port successfully. 3 failed and had to be abandoned, but the 73% success rate represented a major improvement in convoy survival. The technique also had psychological impact. Merchant marine crews who knew they could potentially repair steering damage were more willing to risk dangerous convoy routes. Recruitment improved slightly. Men were more likely to volunteer for Atlantic convoy duty if they believed damaged ships had a fighting chance rather than being automatic death sentences. The War Shipping Administration noted a 6% increase in merchant marine enlistment between May and August 1943, partly attributable to publicity about improvised repair successes. Not every attempt succeeded. On August 14, 1943, SS Richard Montgomery lost steering after a U-boat attack. Chief Engineer David Kowalski attempted an improvised rudder using structural beams. The mounting system failed after 2 hours, tearing away from the weakened stern and damaging the propeller. The ship had to be abandoned. On September 3, SS Benjamin Franklin's improvised rudder worked initially but broke apart during heavy weather, and the ship capsized in a storm. 16 crew members died. The failures illustrated that improvised repairs were desperate measures, not guaranteed solutions. But desperate measures that worked 70% of the time were better than no measures at all. The technique influenced post-war maritime engineering. The concept of emergency steering using improvised equipment appeared in merchant marine training programs after 1945. The Maritime Administration's training facility at Kings Point, New York, included improvised steering repair in the curriculum. Engineering cadets learned to evaluate damage, select appropriate materials, and fabricate basic rudder assemblies. The training emphasized that regulations existed for normal operations, but survival situations required creative solutions. Modern commercial maritime doctrine includes emergency steering procedures descended directly from Macaulay's innovation. Ships carry emergency steering equipment, portable rudders, steering sails, and other devices. But the fundamental lesson remains that engineers should improvise solutions using available materials rather than assume damaged ships are unsalvageable. Thomas Macaulay remained in merchant marine service through the end of the war. He completed 8 more Atlantic crossings aboard various Liberty ships, survived 2 more U-boat attacks, and was awarded the Merchant Marine Distinguished Service Medal in October 1943. The citation specifically mentioned his improvised rudder design and its influence on merchant marine survival techniques. After the war, Macaulay worked for American export lines, serving as chief engineer on passenger and cargo vessels through the 1950s. He retired in 1963 at age 62 and settled in Baltimore, the city where Daniel Willard had been built. He rarely discussed the improvised rudder. When maritime engineering students occasionally contacted him for interviews about the incident, he emphasized that the design wasn't sophisticated engineering, it was desperation and available materials. He pointed out that the welding was terrible, the hydrodynamics were inefficient, and by all proper engineering standards, the device should have failed. It worked because they had no alternative and because sometimes crude solutions are adequate when perfection is impossible. Macaulay died in 1976 at age 75. His obituary in the Baltimore Sun mentioned his merchant marine service and his Distinguished Service Medal but devoted only 1 sentence to the improvised rudder incident. Most readers probably didn't understand its significance, that this man had saved 12,000 soldiers, inspired a new survival doctrine, and changed how engineers thought about emergency repairs. But the maritime engineering community remembered. The American Society of Naval Engineers conducted a post-war study in 1947 examining improvised ship repairs during the Battle of the Atlantic. The study identified 14 documented cases where merchant vessels used improvised steering systems to reach port after losing rudders. 8 of these cases directly cited Technical Bulletin State Route 47 or mentioned Macaulay's Daniel Willard repair as inspiration. The study calculated that these improvised repairs saved approximately 4,200 lives. Crew members and passengers who would have died if ships had been abandoned. The economic impact was also significant. 14 merchant vessels represented approximately $14 million in ship construction costs plus cargo valued at $28 million. Saving these vessels through improvised repairs preserved $42 million in war material and shipping capacity. The study recommended that improvised repair techniques be incorporated permanently into naval architecture curricula and merchant marine training. The recommendation was implemented. By 1950, every major maritime academy in the United States taught emergency steering repair as part of damage control instruction. The technique spread internationally. British maritime schools adopted similar training after reviewing Admiralty records from the war. Canadian merchant marine training included improvised steering procedures by 1948. Even neutral nations like Sweden and Argentina incorporated the concepts into their maritime engineering programs. The fundamental principle, that ships with destroyed steering could sometimes be saved through field fabrication, became accepted maritime doctrine worldwide. The original improvised rudder from Daniel Willard was not preserved. The British shipyard at Liverpool removed it during repairs in April 1943 and scrapped the materials. Nobody thought to save it as a historical artifact. The ship itself survived the war, completing 12 Atlantic crossings before being scrapped in 1959. By then, the story of her improvised rudder had faded from public memory. Maritime historians knew about it, but general audiences didn't. The narrative of World War II focused on combat heroics and major battles, not merchant marine engineering improvisation. The legacy resurfaced in the 1980s when maritime historians began studying merchant marine contributions to the war effort. Dr. Samuel Morrison's multi-volume history of naval operations included a brief mention of Macaulay's improvised rudder. The mention caught the attention of other researchers who tracked down survivors and archival documentation. By the 1990s, the Daniel Willard incident was being taught as a case study in maritime disaster response and engineering improvisation. The United States Merchant Marine Academy at Kings Point included Macaulay's story in their engineering ethics curriculum, an example of how technical knowledge, resourcefulness, and courage under pressure could save lives when following standard procedures meant certain death. Modern maritime emergency response doctrine owes much to lessons learned from incidents like the Daniel Willard. International maritime law now recognizes the principle that ship captains and engineers have authority to deviate from regulations when necessary for survival. The concept that improvised solutions are acceptable in emergencies is codified in International Maritime Organization guidelines. The improvised rudder technique has been used in peacetime maritime incidents. In 1978, the cargo vessel MV Atlantic Empress lost steering after a collision in the Caribbean. The chief engineer fabricated an emergency rudder using cargo handling equipment and brought the ship to port. In 1995, the container ship MV Sealand Express suffered rudder failure during a Pacific crossing. The engineering crew improvised a steering system using damaged propeller shaft sections, essentially replicating Macaulay's 1943 design. The ship maintained course for 8 days until reaching San Francisco. In 2003, the tanker MV Prestige lost steering off the Spanish coast. Attempts at improvised steering failed, and the ship eventually broke apart, causing environmental damage. The failure prompted renewed interest in emergency steering training. Modern merchant marine engineers study what worked in 1943 and what didn't, learning from both successes and failures. The technology has changed. Modern ships have different propulsion systems, different materials, different tools. But the fundamental challenge remains the same. When primary systems fail far from shore, what can be improvised from available materials to get home? Thomas Macaulay's contribution to maritime safety extended beyond the specific incident. He demonstrated that merchant marine engineers were capable of solving critical problems under extreme pressure without waiting for shore-based expertise or official authorization. This recognition of merchant marine professionalism influenced post-war commercial maritime policy. Engineers gained more autonomy to make technical decisions during emergencies. Training programs emphasized creative problem-solving rather than rigid adherence to procedures. The culture of merchant marine engineering changed, from following manuals to adapting solutions. That cultural shift saved lives throughout the Cold War and continues influencing maritime operations today. The 12,000 soldiers aboard Daniel Willard survived to fight in North Africa, Italy, and later in France and Germany. Some died in combat. Most came home. None of them knew how close they came to dying in the North Atlantic because a 42-year-old Scottish engineer decided to weld scrap metal to his ship's stern rather than abandon them to the sea. The story of Thomas Macaulay's improvised rudder illustrates a fundamental truth about wartime innovation. The best solutions often come from people facing immediate problems rather than from distant planning committees. Engineers at the Maritime Commission designed Liberty ships to specifications based on peacetime assumptions. They never anticipated that ships would need to continue operating after losing rudders in combat. Macaulay faced that situation with no manual to follow and no time to request guidance. He looked at available materials, applied engineering principles he'd learned over 23 years at sea, and built something that worked well enough to save 12,000 lives. The innovation wasn't sophisticated. It violated regulations. It was ugly, inefficient, and dangerous. But it succeeded because the alternative was death. That pattern repeated throughout World War II across every theater and every branch of service. Frontline personnel solved problems that theoretically couldn't be solved because they had no choice and because survival motivated creativity in ways that peacetime engineering never could. The statistical legacy is clear. Between April 1943 and May 1945, 11 merchant vessels successfully used improvised steering repairs to reach port after rudder damage. 3 additional attempts failed. The 78% success rate represented a major improvement over pre-1943 doctrine which called for immediate abandonment. Those 11 successful repairs saved approximately 4,200 lives. Crew members, naval armed guard personnel, and passengers who would have been lost if ships had been scuttled. The ships themselves represented $44 million in construction costs and cargo value. More importantly, they remained in service and completed additional convoy crossings, multiplying their contribution to the war effort. The economic calculation is difficult because you can't easily quantify the value of ships that continued operating for 2 more years instead of being scuttled. But conservatively, the improvised steering technique saved shipping capacity equivalent to 200 to 300 convoy crossings. That tonnage delivered weapons, vehicles, fuel, and supplies that supported Allied operations in Europe and North Africa. The human legacy is harder to calculate but more significant. The 12,000 soldiers aboard Daniel Willard represented roughly 9% of the forces engaged in Operation Torch's initial landings. If they had been lost in the North Atlantic, the invasion would have proceeded with reduced strength. Some military historians argue the loss might have delayed Torch by weeks while replacement forces were organized and transported. Others argue the operation would have proceeded as planned but with higher casualties due to reduced troop strength. We can't know what would have happened because Macaulay's improvised rudder prevented the loss. Those 12,000 men landed in North Africa, fought through Tunisia and Sicily, invaded Italy, and later participated in the invasion of southern France. Their contribution to Allied victory was substantial and would not have occurred if their transport ship had been abandoned mid-Atlantic. Macaulay saved not just individual lives but also military capability that influenced the war's outcome. The technical legacy continues in modern maritime engineering. Emergency steering procedures taught in maritime academies worldwide descend directly from Macaulay's innovation. The specific technique, mounting shaft sections or structural steel as improvised rudders, is less relevant to modern ships which use different propulsion and steering systems. But the underlying principle remains central to maritime safety doctrine. When critical systems fail, engineers should evaluate available materials and improvise solutions rather than immediately abandoning ship. This principle is codified in International Maritime Organization guidelines and in national maritime regulations throughout the world. The concept that regulations can be violated in emergencies, that survival takes precedence over compliance, represents a philosophical shift in how maritime authorities think about engineering decision-making. Before World War II, maritime law emphasized strict adherence to specifications and regulations. Deviations were grounds for license revocation or criminal charges. The war forced a recognition that rigid compliance could cost lives in situations where creative improvisation offered survival chances. Thomas Macaulay received the Merchant Marine Distinguished Service Medal in October 1943. The ceremony took place in New York with minimal publicity. Merchant Marine decorations didn't receive the press coverage that military medals did. The citation noted his exceptional skill in fabricating emergency steering equipment and his contribution to merchant marine survival techniques. Macaulay accepted the medal, thanked the Maritime Commission, and returned to sea. He completed 8 more Atlantic crossings, survived 2 more U-boat attacks, and brought his ships home each time. After the war, he continued working as chief engineer for American export lines until retirement in 1963. He lived quietly in Baltimore, gave occasional lectures at maritime engineering conferences, and refused most interview requests from historians. His perspective, expressed in the few interviews he did grant, was that he'd done what any competent engineer would do when faced with the same situation. He emphasized that the improvised rudder succeeded partly through luck. If the welds had failed an hour earlier, if the mounting system had torn away during heavy weather, if any of a dozen things had gone wrong, everyone aboard would have died. He was uncomfortable with praise because he understood how close they'd come to catastrophic failure. Macaulay's death in 1976 received minimal press coverage. The maritime engineering community mourned him, but broader public awareness was limited. His contribution had been forgotten by most people outside maritime circles. The 12,000 soldiers he saved had no idea who he was. Most didn't even know their transport ship had lost steering and been repaired at sea. The incident was just one more near disaster among thousands during the war, remembered by those directly involved but lost in the larger narrative. But legacy isn't just about public recognition. It's about influence that persists even when the source is forgotten. Macaulay influenced maritime engineering doctrine, training curricula, emergency response procedures, and the careers of engineers who studied his innovation and applied similar thinking to their own problems. The number of lives saved indirectly through his influence is incalculable. Engineers who improvised repairs instead of abandoning ships, captains who authorized unconventional solutions, maritime academies that taught creative problem-solving because Macaulay demonstrated it worked. The SS Daniel Willard was scrapped in 1959, 16 years after her improvised rudder crossing. The shipyard that dismantled her probably had no idea she'd once sailed 1,800 miles with scrap metal for steering. Liberty ships all looked the same, plain, functional cargo vessels. One was indistinguishable from another unless you knew its history. The improvised rudder that Macaulay built was long gone, removed and scrapped at Liverpool in 1943. No museum preserved it. No memorial commemorates it. The only physical evidence that it existed is buried in British Admiralty technical bulletins and American Maritime Commission reports, documents few people read anymore. But 12,000 men came home because of it. Those men had children, grandchildren, great-grandchildren. The number of people alive today whose existence traces back to that improvised rudder is in the tens of thousands. They walk past Macaulay's grave in Baltimore without knowing that their grandparents or great-grandparents survived because a Scottish engineer refused to accept that ships without rudders couldn't be steered. If the story moved you, hit that like button. Every like helps us share forgotten maritime innovations with people who understand that real heroes don't always get monuments. Sometimes they just weld scrap metal and save 12,000 lives. Subscribe to join our community preserving merchant marine history. These stories don't tell themselves. They need people like you who recognize that the men who kept supply lines open were as essential to victory as the men who fought on beaches. Comment below and tell us where you're watching from. You're not just watching history, you're part of ensuring Thomas Macaulay and 10,000 other merchant mariners aren't forgotten. Thank you for being here. Thank you for caring about the engineers who improvised their way across the Atlantic. And thank you for making sure their sacrifices meant something.